So far we have talked about means and assumed our data is somewhat normal. But what if our data is categorical or doesn't follow a normal distribution? We have other tools for that. The chi-square test. The chi-square test is the go-to for categorical data. It comes in two main forms. First one is the chi-square goodness of fit. Another one is the chi-square test of independence. Okay, coming to the first test. The chi-square goodness of fit. This test asks, does my sample data fit a certain distribution? For example, if you roll a die 60 times, you would expect each phase to come up about 10 times. This test checks if your observed rolls match that expected distribution. Second one is chi-square test of independence. This test asks, are two categorical variables related? For example, is there a relationship between gender and political party preference? We organize the data into a contingency table and the test tells us if the variables are independent or associated. Another test is Mann-Whitney U-test. When we violate the normality assumption for a two-sample t-test, we use a non-parametric alternative. The Mann-Whitney U-test is exactly that. Instead of comparing means, it compares the distributions of two independent groups by ranking all the data from lowest to highest. It is perfect for when your data is skewed or you are working with ordinal data like survey responses on a scale of 1 to 5. Another test is Wilcoxon's signed rank test. Similarly, the non-parametric alternative to the paired t-test is the Wilcoxon signed rank test. It is used for comparing two related samples like before and after data. When the difference between pairs are not normally distributed, it looks at both the magnitude and the direction of the differences. We have mentioned p-values and alpha a lot. Now let's dive deep into what they really mean and connect them to another vital concept, confidential intervals. P-value and significance level. The p-value is one of the most misinterpreted concepts in statistics. It is not the probability that your hypothesis is correct. It is the probability of seeing data as extreme as you did if the null hypothesis were true. A low p-value means that if the null were true, getting your observed result would be very rare. This rarity is what we interpret as evidence against the null. A significance level is the cutoff you set for this rare event. If alpha equaled 0.05, you are saying if there is less than a 5% chance of seeing this result under the null, I will reject it. Choosing alpha is a trade-off. A lower alpha makes it harder to commit a type 1 error, but it increases your chance of a type 2 error. The power of a test. This leads us to the power of a test. Power is a probability that you will correctly reject a false null hypothesis. In other words, your test ability to detect a real effect. It is calculated as 1 minus beta. You want a powerful test. Power is affected by your sample size, the effect size you are trying to detect, your significance level, and the variability in your data. This is why power analysis is so important before you even start collecting data to make sure your sample is big enough. Confidence intervals. Now let's talk about confidence intervals. If a p-value gives you a binary decision, a confidence interval gives you a range of plausible values for your population parameter. For example, if we are estimating average height, we might say we are 95% confident that the true average height is between 172 centimeters and 178 centimeters. This has a beautiful connection to the hypothesis testing. If our null hypothesis value falls inside that 95% confidence interval, we would fail to reject the null at alpha equals 0.05. If the null value falls outside the interval, we would reject the null. They are two sides of the same coin. The confidence interval gives us more information It tells us not just to reject, but what the effect size might plausibly be. We are ready to level up. What happens when we have more than two groups to compare or when we want to test complex relationships in a regression model? Test is ANOVA, analysis of variance. To compare the means of three or more groups, we use the ANOVA. If you try to do this with multiple t-tests, you would inflate your chance of a type 1 error. ANOVA avoids this by comparing the variance between the groups to the variance within the groups. First one is one-way ANOVA. One-way ANOVA is for a single independent variable with multiple levels. For example, comparing the average sales of three different store layouts. Another one is two-way ANOVA. Two-way ANOVA is for two independent variables. For example, we might want to know if sales are affected by store layout and by the day of the week, and also whether there is interaction between the two. If the ANOVA test is significant, P less than alpha, it tells us that at least one group is different, but not which ones. For that, we need a post hoc test like Kuke's HSD, which performs pairwise comparisons while controlling for the overall error rate. Hypothesis testing in linear regression. Finally, let's connect this to one of the most important tools in data science, that is linear regression. When building a regression model, we are constantly asking, is this relationship real or just noise? T-test for a coefficient. For each predictor variable, we perform a t-test. The null hypothesis is that coefficient for that variable is 0. No effect. A low p-value tells us that this variable is a statistically significant predictor of our outcome, like sales. Another one is f-test for the overall model. We also use an f-test to see if our entire model is useful. The null hypothesis is that none of the predictors are useful, that the model does no better than simply predicting the mean. A significant f-test tells us that our model as a whole explains a significant amount of variance in the outcome. We have covered an immense amount of ground today, from the foundational logic of null and alternative hypothesis through t-test and chi-square test, all the way to the nonsense of p-values, confidence intervals, and advanced models like ANOVA and regression. Here, key takeaways are: first one is hypothesis testing. It is a formal decision making process. It's about weighting evidence, not just getting a yes or no. Another one is respect your assumptions. Every test makes assumptions about your data. Violate them and your results may be meaningless. Third one is don't just look at the p-value. Look at the effect size and the confidence interval. Statistical significance is not the same as practical importance. Fourth one is context is everything. A good data scientist does not just run tests. They understand the business problem and interpret the results within that real world context.